Welcome. In this module, we will look at a few extended resource sharing and binding problems. First problem is related to register banks. A collection of registers generally reside as a bank. So till now we have looked at individual registers, but typically registers reside in a large register file or a bank, say in a RISC machine, and these register banks, so the registers inside these register banks can be accessed through read-write ports. So a collection of registers generally reside inside a bank. Banks have read-write ports for accessing the registers. Two registers in the same bank cannot be accessed at the same time using a single port. So if you have two registers in the same register bank, you cannot access both the registers at the same time using a single port. So you need to have multiple ports in the register bank for multiple accesses to registers in the register bank. So therefore, we need to be aware of the registers' access times when allocating them to banks. So two registers may be put in a bank if and only if these registers have non-overlapping lifetimes. That means that all variables assigned to register R1 say and register R2 say have non-overlapping lifetimes. So all temporary variables assigned to register 1 are in the interval, say this one, and all registers in all temporary variables in register 2 are in another interval, say this one, and these two are non-overlapping. So the registers themselves have non-overlapping lifetimes, or the registers may have overlapping lifetimes but non-overlapping access times. So I cannot access the registers together. That can also happen. So this is a more constrained scenario, that I have overlapping lifetimes but they have non-overlapping access times. None of the registers within the register bank are accessed together using the same port. Okay. Hence we need to optimize size of banks, number of ports, muxes at write ports and demuxes at read ports. I have port A for reading and writing and port B for another reading and writing. So I have two ports, A and B. So I have muxes, circuit points float their outputs on the muxes, and the mux chooses one of the circuit points and places it on the write port of A, and from A I can choose any one of these registers. Similarly, this demux, the demux will read from the read port and choose any one of the circuit points. The port assignment problem is as follows. So we want to assign ports such that mux cost is reduced. An n cross 1 mux is needed to connect n points to one port. If there are two ports and we have n points and each of these n points is connected to one port only, then we have the best possible solution. But the worst case is that we need to connect each point to both the ports. Hence, we want to minimize the number of points connected to both ports. The best case is not always possible. Why? Let us consider 3 time points, and we have 3 register transfer assignments. In time step 1, we have the assignment A equals to X and B equals to Y. In time step 2, we have the assignment C equals to X and D equals to Y. And in time step 3, we have the assignment A equals to Y and C equals to Z. Let us say we use port 1 for this assignment A to X. So I put the value in X to the register A through port 1. Because I have used port 1 at the first time step, for this register transfer I need another port. So I use this I do this register transfer B equals to Y through port 2. Now I come to step 2. X was already connected to port 1. I can connect the same port I can connect through the same port and put the value of x into C in time step 2. Now Z is another new circuit point. Let us say I choose port 2 for Z and do the register transfer Z to D through port 2. Now in time step 3 we see that both Y and Z has been previously allocated to port 2 and at least one of them has to be allocated to port 1 as well to appropriately effect the register transfers at time step 3, because both Y and Z wants to access the two registers in the same register bank at the same time and they are connected to the same port, were previously connected to the same port. So at least one of these points have to be connected to both ports. Now to solve this problem we again have another graph coloring problem. Here the nodes are circuit points. If two points access the same register bank at the same time, we put an edge between them. And that means they access two registers in the same register bank at the same time. We put an edge between them. So when there is an edge between two circuit points, we cannot use the same port for both these circuit points. Therefore, if the graph is bipartite, that is two colorable, if this graph is two colorable, I can use two colors to color this entire graph. That means what do I have? I have two distinct colors, that means two distinct ports, and I have been able to give a color to all vertices while not putting the same color to adjacent vertices. That means I have been able to put each circuit point connected to a single port only, and this is the best possible solution that I have. However, if this best possible solution is not possible, then our job is to remove the minimal number of nodes to make it two colorable. We have if we have two ports. However, this removal of the minimal number of nodes is again an NP complete problem. The removed nodes must be connected to both ports then. So what we do, we first do a two color, try to make the graph bipartite. We try to make a two coloring, and then if this two coloring is not possible, then we try to remove the minimum number of circuit points such that two coloring is possible. And for these circuit points, the remaining circuit points which I had extracted out from the graph must be connected to both ports. Now this is for the two coloring problem. What do we do for the three port assignment problem? With this question posed to you, I come to the end of this module.